let's get started. Okay, first words of who I am. I'm a Bitcoiner. My background is in computer security. I started working to strengthen the Bitcoin security back in 2012, working with Bitcoin core developers. I found many vulnerabilities in Bitcoin. I have probably the record number. And through the years, I worked on several technologies around blockchain, and such as the Rootstock sidechain, which is was the first sidechain developed for Bitcoin. And today I work at IOB Labs, being a scientist and sometimes working on innovation. So this talk, my objective is this talk is not that you become cryptographers, because that's very hard, even for cryptographers, I would say, but that you get an idea of the toolbox of tools or cryptographic schemes that you can use to solve different problems. And so this is very important, because if you are doing something innovative in blockchain, you will probably, think about, oh, how can I do this and keep it private, or how can I do this and make it scalable? And some of these ideas will help you on that. And also I will show you how hard it is to implement some of these ideas, because many times we make mistakes and we implement them wrong. And even Satoshi made a lot of mistakes when he implemented cryptography. So you have to be very, very careful, and obviously try to use standard libraries and all. So we will start with the most simple construction with cryptographic functions. Then we will see proof of work, cryptographic commitments, Merkle trees, digital signatures, some problems with malleability that have plagued the blockchain ecosystem. And then we will switch to advanced schemes, which include obviously SNARKs. So let's start with cryptographic hash functions. So a cryptographic hash function is an algorithm, so it's practical, it's efficient, that maps an arbitrary binary string into a string with a fixed size that is called the digest, and it spreads the changes over the digest. So the output of this hash function look fairly random, and it's difficult to invert. And in blockchain, hash functions are used to authenticate or identify messages unequivocally. Let me change, move this because it's okay here better. So in blockchain, you use it to identify transactions and blocks and any collection of objects. Like if you have a block that has a list of transactions, then you will put those transactions in a Merkle tree. And basically what authenticates a Merkle tree is also a hash function. And also you use it to identify states in the blockchain. For instance, in the case of Ethereum, the whole state at the center point is identified by a single hash, which is the root of a Merkle trie, having all the account balances. You use it to identify snapshots. You use it to identify destination addresses. For instance, in Bitcoin or in Ethereum, what you use is to take the public key and hash it to get a shorter string. And you use it in Bitcoin as proof of work, as we already know. So Bitcoin uses a SHA-2056 square, like it applies 2 times. And Ethereum uses, and Rootstock also uses Kejak 2056. So Satoshi decided to apply it 2 times for 2 reasons. First, it protects from vulnerability. It's not a vulnerability, but just a characteristic of SHA-2. It's called length extension attacks, where you can take a message that is hash and extend it, produce another valid hash, which start with the same prefix. Even if you don't know the prefix, you can do that, which is kind of strange. So if you apply the hash function twice, you don't have this problem. And also, I think Satoshi chose apply it twice to strengthen from unknown weaknesses, like, to make it as secure as possible. Ethereum uses Kejak, which does not have this problem of length extension, and it was later standardized as SHA-3. The trick here is that it's not exactly the same. There are little differences with the constants. So if you want to instantiate this hash function, you have to choose keyjack. You cannot choose SHA-3, even if these algorithms are quite similar, right? And so SHA functions have three cryptographic properties regarding its security. The most important is that it provides first preimage resistance, which means simply like you cannot invert it easily. Like if you are given a hash value H, and it must be computationally very, very difficult to find any message M so that it hashes to H, right? And what's the relation with this with a blockchain? For instance, if we could invert a hash function, we could try to produce proof of work without actually creating any work. So I'm going to go a little bit faster and explain that proof of work is based on hashing multiple times a message until you get a hash digest, which starts with a number of zeros. So if I could do the opposite, like take a message that has a lot of zeros, a hash digest, and then go back and find a preimage, then obviously I can create proof of work without actually doing any work. It's not so easy because basically you have to find a valid block header that maps to that specific hash, but you would break proof of work essentially. Like if you really break the hash function of Bitcoin or Ethereum, you break it completely. For instance, in a case of Bitcoin, each paid to script hash address has the hash of a script, which specifies the conditions under this output can be spent. So basically, if I know this hash digest and I can find another script that maps, that hashes to this script hash, then I can basically change the spending conditions of an output. I break completely Bitcoin. And in the case of Ethereum, is the same. And this also applies to Bitcoin, right? Because to sign a transaction, you don't actually sign the transaction payload. You take the payload, you hash it, you get the digest, which is a hash, and then you sign this digest. So and then you combine the signature with the transaction payload to get the complete transaction. So if I'm able to find another transaction payload that hashes to the same digest, then I can basically reuse your signature, but for a different payload, so I can steal your funds, right? So again, hashing is the most important thing in blockchain. Also, as I mentioned, the transaction ID, it's also a hash. So you take this complete transaction, you hash it one more time, and you get the transaction ID. So if I'm able, to fool this transaction ID, to invert it and find another complete transaction, then I can do a lot of damage, like creating two transactions that map to the same ID. So I can partition the network. So how could I partition the network? Well, let's look at how Bitcoin uses the hash, these IDs to identify transaction. Bitcoin takes all these IDs and puts them in a data structure that it calls a Merkle tree. And each transaction is referenced by the double hash. And also transactions have enough space to put, arbitrary long chosen bytes. So if you want to, try if you had an algorithm to break hashes, you would probably need to store a lot of some data, binary data there, and you have the space in a transaction to do it. And in Ethereum, you have a similar data structure. It's called the Merkle Patricia trie. And if the transaction length is more than 32 bytes, then again, it's identified by its hash. So what you can do is you can take a transaction like that has two different, two transactions, that match to the same hash, and you can create a block having one of these and the other, and both blocks will have the same ID because blocks are also identified by their hash. But basically, you partition the network because there are two parts of the network that are executing a different transaction because they don't see really the difference. The next property is called second preimage resistance, which is basically that if I have a message, obviously I have the hash because I can compute the hash, a message M1, then it should be difficult to find a different input M2 that hashes to the same message, right? And again, at this time, you can break the script to hash because if you if you see one of these addresses being used, then you know a pre-image, then you can find another message if you break it. So what happens with trying to use this to steal funds from Ethereum? In case of Ethereum, you have the mnemonic seed, right, that you convert to a private key, and then with elliptic curve scalar multiplication, you get the public key. You probably already know how this works a little bit. And then you hash it with Keshack 2056, you get actually the Ethereum address, right? So if I could invert the hash, I could get the public key, but still I cannot get the private key because I would need to break the discrete log problem on the elliptic curve. So even if I can kind of break Ethereum in how it identifies blocks, I cannot really, using this steal the funds because I cannot find a private key. I still have one more problem, right? Anyway, it's generally believed to be easier to break the discrete log than to find a pre-image of a hash function. And the third property is called collision resistance. It's basically that I can produce two messages myself having the same hash. And again, this allows me to partition the network because I can, create two blocks with conflicting states that lead to conflicting states. Okay, now I know how hashing works, and I want to create a proof of work. So what is proof of work? Proof of work is a cryptographic proof that a prover proves to others, the verifiers, that a certain amount of specific computational effort has been expended. And the prover can univocally associate the work with a specific input data. In the case of Bitcoin, it would be the block header, right? Because I want to associate the proof of work to a specific block, which means associate it to a specific header. So the basic element of proof of work is that you have a message, right? You have a nonce that you will keep incrementing, and you will hash it over and over until this hash digest begins with a number of zeros, which is generally the property that is used is that its numeric value represented as a big integer is lower than a specific target. Okay, so that gives a little bit more granularity than just counting the zeros, right? And how proof of work is used in blockchain? Well, there are many uses. Of course, the obvious one is Nakamoto consensus, like the consensus protocol that Bitcoin uses. It's based on proof of work, but there are other variants consensus protocols that are also based on proof of work. For example, the ghost algorithm that Ethereum used to use for proof of work was using this construction, and the decor consensus that Rootstock uses is also based on proof of work. And also you can use it, it has been proposed in the blockchain ecosystem to other uses, for instance, to increase the Sybil resistance in P2P communication. Like if I don't want, to have thousands of connections or from unknown source, or one person doing thousands of connections to another peer, I can ask each one of my peers to do a specific proof of work so that I know that, trying to Sybil attack me, trying to connect, to establish many different connections to the same node will have a certain cost. And there are some very interesting variants like memory hard proof of work, which is what Ethereum used, or Litecoin based on script, which force you to use a lot of memory to prove the work. And another interesting variant is called non-outsourceable proof of work, which is interesting because it's a proof of work that you cannot outsource, that you cannot give to any other person to do for you without risking this other person taking your Coinbase, your reward. And this has been proposed to avoid the mining pools, because mining pools actually they centralize the block, choosing the block template, and they outsource the computation. So it's a very interesting proposal. So how it's actually used is in Bitcoin. Well, I already mentioned it. You take the block header, which has this number of fields. it has a Merkle hash of all the transactions that represent all the transactions in the block, and it has the nonce, and you will just keep incrementing the nonce until you get this specific hash, just having a lot of zeros. Well, there are some properties that proof of work needs to have that are very well known. These are the top, the most important properties. It has it has to be moderately difficult to compute. It needs to be trivial to verify. Like if you want, obviously, to create like clients, you need this to be very fast to verify. It has to have a parameterizable cost. Like you should be able to change difficulties and use the same proof of work. You need to generate many of these instances very easily. For instance, at the beginning in 2012, there were people proposing the use of some problem in computational biology, I remember, for proof of work, like finding the 3D structures of molecules. I don't remember exactly. And basically, you cannot generate instances of this problem automatically. So it does not work well for proof of work. Obviously, you need to be able to tie this proof of work to a specific block header, specific data, so that you cannot reuse the proof of work for different things. And this is very important in merge mining, where you have to associate the mining on a secondary chain to a specific block on the primary chain. And you need to be able to create an endless amount of instances, right? But there are other properties that are not very well, discussed, that the Bitcoin proof of work function didn't have, and it was broken. And I worked on breaking these properties in 2014. So these are the not so well known properties. It must be obviously trapdoor free. This is easy, but also it must be optimization free. Like no one should be able to have a secret way to optimize the ways to compute proof of work, because if that is the case, then it's unfair, right? And as long as everyone knows this optimization, there is no problem. But if certain group knows this optimization and the others not, then obviously it becomes completely unfair. So, for instance, there should not be no way to do any pre-computation to do this faster, like a memory CPU trade-off. There should not be any shortcut. The hash rate should be dependent only on the electricity, right? The amount of power I put. And this obviously, if there should not be any hardware architecture, new hardware architecture that makes this function easier to calculate. Another property is that it must be approximation free, which means that this is very interesting, that there should be no way to compute the function, even with some error rate, that makes it faster. Because if there is certain error rate, or so basically you can throw away the solutions that you verify that do not work, but still, if that makes the faster overall, then it's a net gain, right? So I broke this property too. And then it has to have some preventions against block withdrawal attacks on mining pools, which is, I'm not talking about that now. So we broke this fairness property in 2014 by finding an optimization that nobody knew about. And we found also an approximation that nobody knew about. So I will briefly talk about this because it's nice to go on things that you have worked on, so you have these ideas very fresh, and so basically when you do mining, I think there is a one before, yeah. So the SHA-256 hash function splits the message into blocks, 64-byte blocks, then adds a tail block which contains the bit length and the padding, and process each one of these blocks through a function that is called the compression function that takes an initial state, the IV, and combines it with the message and gets the next state, and keeps adding blocks until a finalization stage, which gives you the hash digest. And each of these blocks of the parts of the message are expanded with a message expander, which is not, it's also a kind of complex. It has almost the same complexity as the compression function itself, okay? So how does Bitcoin mining work? Well, the Bitcoin header has two chunks of this of 64 bytes. So the first chunk is generally fixed, like you don't need to change the version, you don't need to change the previous cache or the Merkle root while you are mining. And the second chunk has the nonce, which is this value that you will keep incrementing over and over. So what you actually do is, instead of starting over from the chunk one, the ASIC miners and the Bitcoin code starting from 2011 started from this mid state, which is a point in the middle in the compression function, right? Here you see the mid state. It's one of the states before finalizing before processing all the message blocks. So it's a kind of a shortcut. You start in the middle because the previous part it's already fixed. So you start here in the mid state, you compress this part with the compression function, then you apply SHA-2056 again because Bitcoin applies it twice, and you get the hash digest. So this is the pipeline, how a normal hashing works. The green part is the part that you do only once, which is basically processing the chunk one. You get the mid state, and the part in this pink is what you do all the time. You take the second chunk, you expand it, you pass it through the compressor, you expand it again because of the second application of SHA, you compress it, you get the target, you compare it, right? So a normal SHA miner does this. Takes the mid state, goes through the compressor, expander, and target comparison, and outputs if there is a match. So what we discovered in 2014, we discovered that this message expander takes a lot of space, and there was a way to take out this message expander and put more cores. Like a silicon has thousands of SHA cores that are hashing all the time. So if I save space, I can put more cores. If I can put more cores, I can process more hash rate, right? So we realized that instead of changing the nonce, we could fix the second chunk and start changing the version, because nobody checked the version. Like, there was a lot of bits in the version field that you could actually change and use it as a nonce, okay? So this completely changes how you do the hashing, because now you start with a mid state that is fixed. And sorry, you have an expander, like the second chunk that is fixed, but you change the mid state. So you change the first chunk and make the second chunk fixed. And what you save is this expander that is in green, right? So the rest is the same, but now you have one less expander in this circuit, right? There's some other problems you have to solve regarding potential. If you cannot use the version field, then you have to use some other fields, and that brings other problems. But essentially, all new Bitcoin miners use this technique, so it has become standard. So now there is no improvement that you can do. And if you want to parallelize it in many cores, what you do is, instead of using a fixed expander, you create one expansion using the nonce ones, the nonce one, then another for the nonce two, and you fix that for a specific core, and you keep changing the mid state. So each core is just mining with a fixed nonce instead of a variable nonce. Just this is how you can implement this. And another thing that we did early on was trying to see if we could find an approximation for this SHA algorithm. And what we found, and later it was validated by a paper from the University of Illinois, I think, that if you replace this, so SHA-2056 has a lot of others, right? These squares here with the cross, these are all simple 32-bit others. And what we found is that if we replace this circuit with another circuit that almost always gave this good solution, but sometimes it could be just have some error. And we did that by lowering the length of these of the carry propagation circuit, like taking some gates out. Then the overall hashing would have some error rate, but it would leave room for more cores. So if we could check that the hashing, which solutions were invalid, and keep those valid, then we get a higher hash rate, which is kind of amazing, right? Because in cryptography, what you never want is to have errors. Errors in cryptography always lead to private keys completely compromised. So even a single bit error in ACDSA signing is terrible, right? But here, magically, it's perfect, right? Another interesting case where I took part and there were flaws was in this design of the ET hash, which was the first the Ethereum hashing function that was used when Ethereum was proof of work. So it was designed to be GPU friendly and ASIC kind of agnostic by being memory hard. And I designed one part of this function, not all, but one part, which is called run memo hash, which is basically the part that tries to use a lot of memory. And it was quite well, GPU friendly and ASIC agnostic until 2018, where someone, the Bitmain, realized that there were some optimization that could be done in hardware. They started manufacturing the chips, and as soon mining was dominated by ASICs. And the hardware architecture even kept improving. So current chips are even better than those, because they change how you move data around in the chip. So this is another case where cryptography can be very hard. So yeah, now we have functions, and we want to go one step higher. So we want to do cryptographic commitments. So a cryptographic scheme allows one party to commit to a chosen value or statement or message while keeping it hidden to others, and with the ability to reveal this committed value later, right? They are generally built using a hash function with a message with a randomization function, because since everyone can compute a hash function, and what you don't want anyone to try to see which your input is. So you basically take a fixed size message, you add or append a random value that only you hash it, and you get a number that you can show the others. And when you want to reveal this relation, you have to reveal this message and the random value. Anyone can verify that you wouldn't be able, without a lot of computation, to change the commitment, right? And it is used in a lot of protocols in blockchain. And it can be used to prevent front running. Like it's a one very well-known use is, for instance, in Ethereum, ENS domain acquisition protocol. So ENS is a domain system over Ethereum where you can buy domains. And but if I want to buy a domain and I just post the transaction saying, hey, want to buy this new domain, so anyone can see my transaction and can grab the same domain, create a transaction with a higher fee and steal it. So to protect from that, what I would do is send a transaction that say, okay, I want to buy the domain, and I just give the hash or a commitment, sorry, of this domain name. And I wait a lot of blocks to confirm the transaction to make sure that I'm the first to do this commitment. And then, later I can open my commitment and say, okay, the domain I wanted to buy is this, here is the proof. And then the protocol can say if anyone else was trying to acquire the same domain, and if there's nobody, then it can give it to me, and I'm protected from this from running. It's also used to generate kind of unpredictable randomness in consensus. And it is used in Ethereum proof of stake with a construction called RunDAO, where you have a lot of parties. Each one of the party commits to a secret number. And then we can, at a later time, we can open all these commitments and hash them together. And what we get is a kind of a random, pseudo-random number that it's difficult to predict. Okay. So with this construction, we can build Merkle trees and tries. And a Merkle tree, similar to a hash function, authenticates a message. But generally, this is built as a list of smaller ones. Like, I don't want to authenticate a linear message, but generally I have a lot of small messages that I want to authenticate all together and in a specific order. And what is interesting is that a Merkle tree allows you to proving the inclusion of certain elements in this tree without revealing all the elements, and in logarithmic size, and in logarithmic time also, or logarithmic computation. So even if I have billions of elements and I want to prove that one particular element is part of this collection, then I can give you, the logarithm of billion, 30 nodes on this tree, and prove that to you. Okay. It has many use cases in blockchain. As I mentioned before, it is using to authenticate a list of transactions that are in blocks. It is used also in blockchain to succinctly define a long list of payment receivers. For instance, there were cases for airdrops where, I want to airdrop to 1 million users or 1,000 users, but I don't want to give all this information to the blockchain, either for privacy reasons or because I don't want to pay the gas cost in Ethereum to do this. But I still want any one of these participants to be able to prove that they can receive this airdrop. So what I create is a Merkle tree of all these destination addresses that are that can receive the airdrop, and then I just post the root on the smart contract, and then anyone that knows this tree can find a proof, create this proof, and send this proof to the blockchain and pay themselves for the cost of getting this airdrop. It was also used for Ethereum when it switched to proof of stake, to let parties in the proof of blockchains to register to be stakers in the proof of stake. All the parties where there was a collection of a Merkle tree of all the parties that wanted to participate in proof of stake. And another use is what is called SPV clients in Bitcoin terms, which are like clients that they don't need to process every block, but they just listen and try to follow the chain with the hasher, the highest hash rate or the highest cumulative work. But at the same time, they want to be informed is there is a transaction that is specific to them. And then they can use these inclusion proofs in the Merkle tree so that anyone can prove to a SPV client that there is a specific transaction for them. Obviously, there are variants that are used today in blockchain. The randomized Patricia trie is used on Ethereum. It's different from a Merkle tree because a Merkle tree is generally it's a complete tree, or like a binary tree, while a Patricia trie can have different keys of different length. Another variant that is used and will be used in Ethereum is the sparse Merkle tree, which is basically a tree that you can fill in different parts also, because it's filled with zeros. These are constructions that are used today. And I also happen to work finding vulnerabilities in Merkle trees. And one of the vulnerabilities I found in 2018 is it's very important and generate a lot of problems for SPV clients and for bridges, for bridges that connect with Bitcoin. It's about the way that the Bitcoin Merkle tree is created. So the Bitcoin Merkle tree it's very specific because it doesn't have any distinguisher between the intermediate nodes and the terminal nodes. So basically, you take the transaction, you hash them, you get the 32-byte identifier, you concatenate with the another identifier, and you hash it, and you get to the next level, and so on, so on, so on, you get to the root hash. But if I want to show you that a certain transaction, it's part of this Merkle tree, I could try to cheat you, and instead of telling you a terminal transaction, I could say, okay, I will try to convince you that an intermediate node is actually a transaction. And since there is no prefix on these nodes that set them apart, if I'm able to build a Bitcoin transaction that is only 64 bytes in length, then I can cheat. And so this was very important for breaches. For instance, the Rootstock breach, the TBTC breach also had to be protected from these. The inter-BTC breach, all of these breaches are protected from this Bitcoin flaw, where basically you can reinterpret nodes as transaction, or what is worse, that I also found, reinterpret a transaction as a node and extend the tree one step, even depth. Right? So what I mentioned about inclusion proofs, an inclusion proof is this it's a collection of hashes that if I combine with the hash of the transaction in the different levels, I get to the root. And yeah, so that's an inclusion proof. Also, there was another vulnerability in the Bitcoin Merkle tree that was fixed in 2012, is that when the tree was not complete, what Bitcoin did was add another copy of the previous node. Like, for instance, in this case, if there was no 7th and 8th element in this tree, or more, then in the previous level, it would clone the F node and put it again there. And what somebody realized is that essentially this makes no distinction between a block having only transactions 1 to 6 and a block having transactions 1 to 6 and then repeating 5 and 6, because basically you get the same node. And Bitcoin has no specific field to tell you how many transactions the block has, right? Or the depth of this tree. So these two trees are identical. And what you can do with two identical trees that, you know, have different payloads is that I can give some nodes as a version of this block, having, you know, the transactions, this transaction 5 and 6 repeated, and the other half of the network I can give the other. And what happens is that the nodes that receive this block with repeated transaction will think that this block is invalid, because, you know, Bitcoin you cannot repeat transactions. No, in Ethereum you cannot also, but in Bitcoin you cannot. So they will mark this block as invalid, and if they do, they will never ever accept this chain as the honest chain, while the other half will do, because they received the copy not having those transactions. So this was an attack on Bitcoin. So yeah, I talked about this, the possibility of reinterpreting the node as a transaction as a node. So I'm going to skip this. This is about the vulnerability I mentioned. And yeah, this again, more about adding more layers. Okay, so we don't have much time. Yeah, so what about digital signatures? Yeah, you know, digital signatures are very important for blockchain. A digital signature is a mathematical scheme for verifying the authenticity of digital message or document. This is the Wikipedia definition. A valid digital signature of message gives a recipient confidence that the message came from a sender known to the recipient. So you already must know who this sender is. You must have a public key that identifies this recipient. And it is used obviously to authenticate user transactions. And also it is used for instance, for anonymous cash. There are certain schemes like the Xiaomi eCash, the Fedmin protocol, that use specific variants of digital signatures. In particular, they use a variant of digital signature called blind signatures, which is very interesting. It's a construction where you are giving a message that is kind of randomized. So you sign the message, but you actually do not know actually which message you sign. So it allows you to create like authenticated messages where the person who signed does not really know the look of this message, how this message looks, and it's used for anonymous cash. There is another variant called aggregate signatures. It's very interesting, where you can combine multiple signatures in a single signature, and this is used for scaling blockchains, making sure that blocks are shorter and are faster to process. And there are a lot of schemes of signature schemes. The most used on blockchain are ACDSA and SNARK. Schnorr is better than ACDSA almost in anything. It's faster. It has a very nice security proof. It also allows more better aggregation. But when Bitcoin was designed, the Schnorr scheme was protected still by a patent. So I think that's why Satoshi decided to use the ACDSA scheme. But then Bitcoin switched to Schnorr with SegWit. It allows, it just uses Schnorr. So you can still use ACDSA, but if you use SegWit, you are forced to switch to Schnorr. And then there are other schemes like BLS, which allow very nice signature aggregation, RSA, and for instance, Merkle Winternitz, which has been used in certain blockchains. I read it, which is quantum computing resistant, while the others are not. So yeah, so both, what I say, both Bitcoin and Ethereum use ASA for signing transactions, and both of these schemes are based security on the discrete logarithm problem on elliptic curves, and these schemes are not protected from powerful quantum computers. So if we find, room temperature superconductor, and then that leads to an efficient quantum computers, then we will have to switch the signature schemes of all blockchains. And some people have been working on how to actually change the signature scheme of Bitcoin. For instance, how can you do this in phases so that while the construction is still somehow secure and you could switch to another construction. It's very hard, but it can be done. So I think we will have time to switch if that comes. And so yeah, there are certain security concerns when you do when you use ACDSA. The most important, and has caused a lot of headaches, it's the generation of keys, of private keys. There is this multiplication of a point in the elliptic curve by a scalar, and how you choose this scalar, this is your secret key. And if you don't take enough entropy or good entropy, and you choose it, by a flawed a pseudo-random generator number that does not take good entropy from hardware generator or for whatever, and then you will end up with a key that can be guessed, and then the whole security will be broken. So sometimes people have on purpose created implementations that use restricted random sources to try to cheat, to try to steal other people's money. This has happened. Sometimes it's human error that creates this key with low entropy. And if we take a look at how it is used to sign, there are also other problems that you have to be very careful. So for signing with the ACDSA, you have to choose a fresh key, which is called the nonce. So you basically cannot reveal this nonce ever. Like if you reveal a single bit of the nonce, you will someone can steal your private key, and you cannot repeat it, right? If you repeat the nonce on two signatures, then obviously the private key will be able to be recovered, and this has huge implications. Like if you have to make sure that if you, for instance, if you start from a backup of the system, and then somehow the nonce was in a state, and then you reuse the nonce, you lose all your money, all your security. So it's very important not to reuse the nonce. And then there are other problems that hardware wallets must lead with. One is this side channel attacks, where this operation where you actually multiply this private key with this value R, and if you do it on a standard computer or with code that is not specifically protected with for side channel attacks, then there's a lot of ways that an attacker that is physically in control of your machine, like measuring the electromagnetic emissions, that is measuring your electrical consumption, that is even listening to your computer. There are a lot of ways that the attacker could extract your secret. And finally, there is still another problem, which is called the covert channel attacks, where the hardware wallet generally could potentially leak information very slowly about your private key, and you will notice. So the best hardware wallets use algorithm called anti-exfiltration techniques that prevent the hardware wallet from leaking any data about the private key. And to protect from this non-repetition problem, there is an RFC 6979, which makes this value deterministic based on the message and the private key so that you will never repeat it, right? So these are the problems. And here I'm showing you what is the setup that people use to extract secrets. This is a tracer hardware wallet using side channels attack. In this case, the guy is measuring the power consumption, and it allows you to extract the private key. Obviously, this was in a previous version of the tracer hardware wallet. Now I think it's fully protected. Okay, there is a lot of mistakes that people do when using signatures generally in smart contracts. First, one is assuming the signature uniquely identifies the message and the public key. And I found, for instance, the first these are problems are called malleability problems, where you basically change the signature or change the public key or the message to try to cheat in some way. And so one of the problems that I detected in the early years of Bitcoin was that you could take a signature and either change the encoding of the signature or change the yes value of the signature, and you will get a different signature, but that authenticates the same message with the same public key. And because of the transaction ID was based on the signature, you would change the transaction ID, and then it would lead to a lot of problems, like exchanges not recognizing their own transactions because the transaction ID had changed. It is believed that this I don't remember the name, the Carpels exchange, Mt. Gox. It is believed that it was hacked because it was attacked with a signature malleability attack. I don't know for sure, but he said so. And there are other more subtle attacks regarding this signature. Is that assuming that the signature uniquely identifies the message. So it's possible to build a signature that verifies two chosen messages with two different keys with known private keys. So there is a method, and this is the paper where this method is explained to do this. So basically, the signature does not uniquely identifies anything, right? It just proves that if you have a certain message and a certain public key, then that public key has signed that message and nothing more. So these are all malleability attacks from people that that try to use properties of signatures that are not really the security properties of this scheme, right? Okay, so what about the security of signatures with the quantum computers, where basically they break? There is an algorithm called the modified Shor algorithm that allows you, if you have a powerful quantum computer with 1,000 of bits of qubits, you will be able to find a discrete logarithm. And there is places where in Bitcoin and Ethereum where you can see the public key. There was Bitcoin had a pay to public key transaction originally, where the public key was just posted in the script public key, and so basically with quantum computers you could just steal. In pay to script cache, the public key is not directly visible until you use that address for the first time. When you use it, then it will be known. So again, it will be completely broken for addresses that you have already used. And in the case of Ethereum, if you could, break this discrete log problem, you could take the public key, find the private key, and of course you could steal the funds. But again, you need its public key to be public, and the public key is not public until you do your first transaction spending funds from an account. So if you don't touch your account, never, I mean, if you never spend from a specific wallet, then it would be theoretically protected from this problem. Okay, so I've not covered. I think I've covered. We are almost getting to the end, but I've covered like half of the material I had. So I will keep for 5 minutes more, and then I will discuss with James if there is a possibility to extend it some other day, maybe tomorrow, or to finish with the other topics which are as interesting as this. I'm sorry of not calculating the time good. So one of the problems with malleability I found in the very early Bitcoin system, where this is actually the first signature malleability problem I found, and this was epic. Like Satoshi had put on Bitcoin an alert system to be able to alert all nodes if there was a problem, like, you know, vulnerability in the code, people had to upgrade, anything. So he put this system, and each node, when it connected to a different node, it will broadcast this alert, all the alerts it had received, it will broadcast to all the nodes as soon as the new node connected to this. Each alert has an ID, so that nodes will not forward the ID as the same alert several times, because in that case, the same alert would flood the network, right? But I found that, you know, these signatures were malleable, and if I change the signature, then I would get a different alert with a different ID. So what I was able to do is generate very fast billions of valid alerts and spread them all over the network, and they all looked that they were, you know, signed by Satoshi's key. You cannot just, I mean, they had all the same data, but different signature and different ID. And what happens was that the node were not prepared to have billions of these messages in memory, so they will just core dump. But before core dump, they will spread all the alert to all the other nodes. So the whole network, the whole nodes in the network will core dump. And if you try, you know, to bring a node up, the peers will bomb you with this alert, and your node would go down again. So it would completely break the network. So I never tried it in the real Bitcoin network, of course. I reported it, and so they solved it before it caused any harm. Yeah, and another problem that I mentioned before is the problem with transaction IDs in Bitcoin. Again, there's signature malleability, and this is solved by SegWit, right? Okay. So I think this is maybe a moment to stop, so I can leave kind of half of the conversation for another moment. What do you think, James?
I think that's perfect. Do we want to take questions if there's any questions in the crowd? This was fantastic. We have Jay, then Cordy.
I think I'm not the first. I think it's yeah, I guess I'm first. So my question would be that you mentioned it's possible to reward the it's probable to redo a signature without a private key, right? But is that
to what? Sorry.
There is one page that's saying that we can have the same signature but for different message or for different.
Yes.
Yeah, could you go back to that page?
Yes. No, it was sorry, it's later. Sorry.
Yeah, I think it's in the ECDSA part.
Yeah, here.
Yeah, I'm actually quite confused because I think signature is actually produced by the private key, and if we save the private key, it's never leak. The signature and the messages should be very hard to have another signature, wasn't that?
Well, that's the problem, that if I'm able to choose the messages and choose the private keys, I can create one signature that verifies the two different messages with two different private keys that I know. This is not, this is, okay? So generally what you do when you have a signature, you have a specific message that you want to verify with a specific public key.
Yes.
But if you want to assume that a signature per se will be linked to a specific message or a specific public key, that's not the case. You can do, and you can check this paper where it shows how to do it. It has some problem, like if you do it, then you also leak your private key. but as long as nobody notices it, then you can do it.
Oh, I see. So the problem here is that if you leak your private key, or you have your private key, you want to do something else, it's possible. But as long as you keep the private key safe, no one can have a signature from that private key, right? Is that from yourself?
So if you do this trick, like try to create a signature with two private keys,
yes,
the trick reveals the private keys. That's the flaw of the trick. But essentially, if you want to attack a certain contract, for instance, there was a contract in Ethereum that had this vulnerability. You wouldn't care about, revealing the private keys, because the attack would be so fast that, by the time anyone noticed that there is a way to obtain the private key would have no funds and the money would be stolen, right? So this is a trick that I just want to show you how bad you can use a signature scheme, right?
I see. Yeah, so that is
so for instance, in Ethereum has a thing called signature recovery, which actually you don't give the verifier the public key. Signature recovery, no, public key recovery. So what you give the verifier is the message and the signature, and the public key is extracted from the signature and the message, which actually means that if I change the message, then I can, for the same signature, I will be able to get a different public key that maps to the same signature for the different message very easily. That doesn't mean that I know the private key related to that public key, but I'm able to do that, right? I'm able to make this signature work for another public key and another message. So that's another way to fool the smart contracts that try to use the signature as an identifier of something.
I see. Okay, that is possible. And also, another question about the mining part. You mentioned that a new version of mining could change the version rather than the nonce, right?
Yes, so let me go back. Yeah, here. So what's your question?
Yeah, my question would be, what would that do good to miner, because the hash rate is still the same. You still got the same chance to get reward. Yeah,
so this is, let's go back. This is this is how a core works without ASIC boost, which is this optimization. You see there is one expander, one compressor, one expander, and one compressor. So 2 compressors, 2 expanders. And each one of these is approximately the same size in the die, right? And this approximately the same number of gates, okay? So you increment the nonce and you have to go through all these 4 stages, which are sequential, until you get the target comparison. Now, let's take a look at how it works with ASIC boost. There are 3 blocks: compressor, expander, and compressor. So 2 compressors, only 1 expander, because the other expander is out. It's not part of the loop. It's not part of the hashing loop, right? So we've moved the other out. So now I've saved 25% of the space. I can put 25 more cores. Well, it's not actually 25 because you need to add certain circuits to compensate and do some other stuff, but maybe it's 15%. more cores. If you put 15% more cores, you get 15% more hash rate, right?
Yes.
And the power consumption will be approximately the same because you've taken a circuit which is always active and put another circuit which is always active, right?
I see. Yeah, that makes sense. Yes. Thank you. Thank you for answering that. That would be all my questions. Thank you.
Yes.
Fantastic. We have one more question before we have Alejandro come up to the stage. We have Cordy.
All right. Hello, Sergio. You guys?
Hello.
Yes. So, yeah. Sergio, what's up, Sergio? So I have a few questions. I believe I'm a big believer in following like for 4 years now. I believe
Sorry, the sound breaks a little bit, but I'm trying to hear.
Get rid of my headphones. This is probably better. Do you guys hear me now?
Yeah.
All right, much better. Yeah, so like I was saying, I'm a big believer in Rootstock. I've been following Rootstock for 4 years now. I see it as the central hub, and it connects to blockchains like a spider web in that sense, right? So we basically created me and my team created a blockchain domain. The whole goal is to use identity, gaming, and education to bring mass adoption, right? So one thing that we try to do is bring ordinals to Rootstock and use that metadata and connect it to our identities. So you mentioned a bridge idea with ordinals and Rootstock. What's the process for that like, and how are we able to bring that metadata from ordinals to Rootstock? Because from your tweet, it's something where the inscriptions are unchained. Two transactions are unchained, and they could be traded on Rootstock. How would that work? Okay. Because our goal is to bring the inscriptions under our identity and have identities owned.
Okay, if I understood correctly the question is how the bridge to bridge inscriptions from Bitcoin to Rootstock works. And
correct.
Yeah. So recently I made this proposal because I thought there will be a lot of teams wanting to do things mixing ordinals and inscriptions into Rootstock and trading them because it's cheaper, it's better. And so I created this specification. We call it obviously RSKIP, improvement proposal, that accomplished this. So what we do is the following. Normally, what the Rootstock bridge does is it assumes that any Bitcoin that goes in is fungible. So it mixes them with the other Bitcoins. And when you get out of Rootstock, when you peg out, you are basically given some other Bitcoins, not the same that you deposit, right? Because these are mixed, there's a change, whatever. What I added to the bridge is the possibility to park specific UTXOs. So the bridge is kind of agnostic to the metadata, but you can park a specific UTXO and then control it from Rootstock, sell it, trade it, whatever, so that anyone can then move that specific UTXO again out of Rootstock. So I think more about parking. So the bridge doesn't know anything about the metadata of the inscription. And if you want to take the metadata, you can do that. You can access the metadata if you want, because Rootstock, the bridge has a full view of the Bitcoin blockchain. So you could actually try to prove things like there is a blog that contains certain image on Rootstock, but the bridge does not try to get that information for you. So what I think is that that should be responsibility of the client. Like if I create a site where people can trade and on Rootstock, and then it detects that this specific UTXO is parked, then it goes to the Bitcoin blockchain and it grabs the metadata and then it uses it. Because I think that in the long term, people will bring those inscriptions back to Bitcoin. So I think more of Rootstock as a platform to trade these ordinals than a platform so that they be there forever, right? So I always, generally, when we make changes to the bridge is the most critical piece of code in Rootstock, and probably in any project. Like bridges are the most sensitive thing in any project. So when we do changes to bridges, we try to minimize the change set to very specific, and to leave all to the application layer. So that's what we tried with the inscriptions bridge.
Yes, and I also read that it's going to be a way to bridge out other non-fungible assets as well, right? In that sense.
Yeah, yeah. Anything that is related to a specific UTXO, you can park. I call it park because I imagine something like that happening. So you can basically link that to Rootstock, manage it from Rootstock, trade it, or you could split it also in shares or anything you want to do. And then sometime in the future, you sell it back, or you move it back into Bitcoin, or you unlock or unpark this so that it can be moved into Bitcoin. And one of the difference between pegging out Bitcoins and pegging out inscriptions or these parked UTXOs is that we have a limitation where you cannot peg out Bitcoins to any address, only address that you control. And this is for making sure that you don't do arbitrary payments across the bridge. But in the case of inscriptions, you don't have the limitations because inscriptions are not money. So you can actually peg in and peg out to any address freely.
Perfect. And also, there was one thing I want to mention is the use of flyover protocol. How would that work?
Sorry, what?
Flyover protocol.
I cannot understand. Maybe you can type it.
Flyover protocol.
Flyover. Yes. Yeah. Yes. What do you want to know about flyover?
Yes. How would that work with the non-fungible bridges like ordinals and then NFT?
What we decided to do, Rootstock is managing or has in custody with a POPEG millions, hundreds of millions of dollars, and we don't want to mix the same private keys that move these $100 million with the private keys that move the inscriptions. That would be a very bad security idea. Like, it's always good to separate domains with having different security levels. So what we did for inscriptions, that we shortened the number of confirmation blocks for getting in and getting out. So I think you can get in with just 6 confirmations and out for. So basically, when you peg in Bitcoins, you have to wait 10 hours. And when you peg out more than a day in Rootstock. But if you are pegging in or pegging out ordinals, then it's very fast. I think it takes 1 hour in and 1 hour out with the current design. So since we are using different private keys to control them, and it's still a federation, it's still a multi-sig, but with separate private keys, then we can lower the security to a security that is, in the same level of the amount of money that these inscriptions are valued, right?
Yes, because I would love to use that as a way to provide liquidity. That could be another way to generate revenue for my company, to provide liquidity for using flyover protocol. And that's something that's very, I can't wait for that to make sense, to be out there and use it.
Yeah, flyover, it works for Bitcoins because it basically allows anyone to advance the funds. But in the case of an ordinal, you cannot advance an ordinal, but there's no other ordinals that you can, it's not fungible. So flyover lets you peg in and peg out very fast, but only for Bitcoins. And ordinals have this specific restricted confirmation time, which is good. It's enough for this to be, the user experience to be kind of nice. Not a day of.
Thank you so much, Sergio. And I'll definitely love to get in touch with you again about just ordinals. It's good to see what we can do about ordinals and how to, bring in more attention with ordinals in the Bitcoin community around the Rootstock ecosystem.
Love to talk. Yes, contact me, and I love to. Okay.